The answer that's there has a typo in it. And of course, they all have the typo. It's supposed to be dx over dy. I didn't get that corrected, but they should all be dx over dy. The 5 in the numerator is not supposed to be 5, it's supposed to be negative x. The denominator is correct.
Replace the 5 with the negative x.
Yes.
How'd you get that? I got the right answer on that one.
Unless I made a math mistake, because I tried working it out again. Let's see what you did. 5 minus x times 1 minus.
5 plus x times 1.
Ah, yes, yes. I forgot my negative one. Which means that would be, this negative cancels out. Okay. Yeah, okay. So no, there is not a correction. Double check your derivatives. There is not a correction. That is a 5.
Can you go over that maybe?
No, because I want to give you the grade for it. You'll find it.
I think that's the derivative that.
No, that actually, the answer that's there is correct. The answer that's there on that one is correct. Okay? I missed a negative sign, and I missed it when I worked it with you too. So there's a -1 that you need to take into account in the numerator. Let me double check the arithmetic, because I know the process that it was right, but I didn't double check the
This one
arithmetic.
too? I mean,
That one, yes, your answers are correct on that one. That one's the other one I was gonna tell you.
that makes sense.
So let's see.
That makes sense.
You said number 5, the second tangent line, B?
Yeah.
So that.
Okay.
Number 5 was the one that should have been minus instead of plus.
Yeah.
Yeah. Yeah, it's a difference in signs. So I'll tell you the correction on that one too.
So this is essentially 5 plus x times -1 times x. So it's minus.
Yeah, on number 5, there's a sign mistake.
See, that's this -1, this is to put this trig line sign with negative 1. So it's -5 minus x, and then times -1 plus positive 5.
But on number 7, there's a huge mistake.
That's distributing -1, and then this negative sign is distributing -1. So, plus, translate this to pluses. That makes sense.
So there's the big correction, and I did not catch it until I was going over it with Katie, and I'll apologize to you for the lack of due diligence on the people that wrote the solutions manual, because that's the answers they put in the solutions manual. And I didn't double check it before I gave it to you as being the correct answer. But that is those are correct answers for number 2, number 5, and number 7. And the reason I bring that up is I'm gonna leave that open until tomorrow night, give you a chance to correct it if you need to, or to go ahead and submit it if you haven't. Because if everyone does well on this, and I think everyone will if they go ahead and submit it, then I would actually prefer to count this as an extra test grade rather than a quiz grade. So let's see what happens.
If we do well?
If you do well, I'll count it as a chapter 13, 14 test grade rather than a quiz grade.
Can we do it certificate?
No, you still have to have a test over chapter 15. I don't want you to go into the final exam and that being the only time you've been tested over chapter 15. Because there are chapter 15 problems on the final. Okay? But we will count it as a test grade over 13 and 14 as long as the class average is 80 or above. Let's put it that way. And people that don't turn it in, I'm not going to count them as zeros. They're just going to get their 0, because if you don't turn it in, you don't turn it in. So, and if anybody needs it, I'll put this back up there, but I will post this in Shobi too, so that you'll know what your correct answers are that you're supposed to be aiming
So
at.
that's due tomorrow?
It's due tomorrow night. I haven't changed the date, but don't worry about it. I will change the date. So let's kind of get back into integrals. As soon as I figure out where I put my notes. Yeah, I picked them up with the quiz.
Are there class notes in Shobi?
Yes. Yeah, there's in there where it says notes and lecture. And then I'm adding to the lecture as I go along.
Oh, yeah, okay.
Okay? So, with the rules for exponential functions, and just a reminder of what those rules are, the integral of e to the x dx is equal to e to the x plus a constant. And the integral of a to the x dx, where a is a number other than e, as long as a is positive, and not equal to 1. There we go. Then that integral is a to the x over ln a. And again, plus the constant. Now, if there happened to be a multiplier in front of x, then that multiplier comes down just as it normally would as the derivative of the power. So if this, for example, had been e to the 2x dx, then this would have been 2 e to the x dx. I'm sorry, it would have been divided by 2, not multiplied by 2, because it's the derivative of power. So if this had been just as a, any constant in front of there, then that integral would have been changed only by the fact that you're going to divide that by k. And the same thing here, if there had been a constant in front of your x, then that constant is going to come down in the denominator and multiply times the natural log. So that's the only difference between the two rules. So, for example, we have 4 over x. The integral of 4 over x. Excuse me. And just to avoid the distraction, I'm going to take the 4 and pull that out in front of the integral and just do the integral of 1 over x dx. And so the integral of 1 over x dx is the natural log of x. And you just bring that 4 along as a hitchhiker and multiply by it. And then you add your constant. Now, the textbook is kind of loose when they insist that you do or don't do this. What you need to keep in mind is that they're redundant. You don't absolutely always have to have them, but sometimes my math lab may count off if you don't have them. The absolute value of x, it has to be the absolute value of x, but that's because you can't take the log of a negative number. So whatever x is, if it happened to be a negative number, you're going to have to take its absolute value. Like if you're trying to substitute in a value of x, you'd have to actually take the absolute value of whatever negative value x might have. So they don't really spell that out very much when they do the derivative, but you do need to take into account that that does need to be a positive number you're taking the natural log of. You cannot take the natural log of negative numbers. And then for our second example, we actually have 2 terms, which again, we would break that up into 2 pieces. That would be the integral of negative 5 over x plus the integral of e to the negative 2x, and both of those have dx. They have their own dx, indicating that they're derivatives. And just like we did with the 1 over x here and putting the 4 out front, we do the same thing here. We pull that negative 5 out front just to make life easier. So that'd be negative 5 times 1 over x dx plus the integral of e to the negative 2x dx. And since the integral of 1 over x is the natural log of x, and I'll put the absolute value bars in there because if x were negative, you'd need them. And then you multiply that by your negative 5, because remember your coefficients are always just hitchhikers, plus the integral of e to the negative 2x is going to be e to the negative 2x and then you're going to divide by that negative 2. And then that's going to be plus a constant. Now that can be rewritten a number of different ways, but there's nothing wrong with writing it that way. That's perfectly fine. It might look better to you if you wrote it this way. Since this is negative, make that a subtraction. And since this is 1 over 2, just pull it out and call it 1/2 times e to the negative 2x plus c. And that may be more like what an answer that you would see in the back of the textbook if they totally simplified it. So remember, integration is derivatives in reverse. You have the derivative, go back and find what it came from. And there are applications for it, even though we've not come to some of the best stuff about them yet. We'll get into the best stuff about them when we get into section 15.3. Suppose a publishing company's found that the marginal cost, what does that word marginal tell you? That means that this is a derivative. at a level of production of X thousand books is given by C prime of X is equal to 50 over the square root of X. So that's your derivative. And that the fixed cost, that's the cost before the first book can be produced, is $2,500. It says find the cost function, C of X. Well, first thing we need to do is we need to find the antiderivative C prime of X. So the antiderivative is more easily found if we'll pull the 50 out in front and treat it as a constant coefficient. And then 1 over the square root of X is better if we write it as X to the negative 1/2 power. And then that means that's going to be equal to the derivative of X to the negative 1/2 power. Negative 1/2 plus 1 is going to be X to the positive 1/2 power. And then we're going to actually divide that by 1/2, which is the same as multiplying it by 2. And then we're going to actually keep that 50 then, that came from the coefficient. And of course we know that we'll have some constant. So 2 times 50 is going to be 100 X to the 1/2 power plus some constant. We don't know what the constant is. So that tells us that this is our cost function. And here I'm writing in the word constant rather than using the C so that you don't confuse it with the C of X. And of course you know that X to the 1/2 power is the same as the square root of X, so we could just take square root, but I'm going to leave it at this for right now. But now this is what's actually called an initial value problem. It's a problem where they actually give you the information to find out what that constant is. Because it says the cost before the first book, so that means X is 0. Is $25,000. So when you make no books, this becomes 0. And the value of your function at that point is $25,000. That means your constant is actually $25,000. And that means then that your cost function, C of X, is equal to 100 times X to the 1/2 or the square root of X, whichever way you want to put it, plus 25,000, and that's dollars. And that is your cost model there. C of X then is equal to 100 times the square root of X plus $25,000 for making or producing X thousand books. Don't forget your units. Any questions? So there's one really good use of being able to take an antiderivative. If you're given a marginal cost, you can actually find the cost function from the marginal cost. And our next example is an example of a demand problem. So suppose that the marginal revenue from a product, and there's that word marginal again, that tells us we've got a derivative, is given by 400 e to the negative 0.1 q plus 8, and q is the number of products produced. And it says they want us to find the revenue function. Well, this is the derivative of revenue. So there's your derivative. And we need to integrate that derivative to get back the actual revenue function. And remember, in this case, it's dq. And again, your 400 is just going to tag along because it's just a coefficient. And then the derivative of e to the negative 0.01q is e to the negative 0.1q divided by that coefficient, which is 0.1. And then the integral of 8 dq is going to be 8q. If you've got the integral of a constant, you basically just put the variable back in. And then that's plus c for our constant of integration. And then in order to figure out what c is, we take into account that if q is equal to 0, your revenue is also equal to 0. So if this is our revenue function, then it's equal to 0 if q is equal to 0. So what that means is that we have 0 is equal to 400 e to the negative 0.1 times 0 over negative 0.1 plus 8 times 0 plus the constant. And since this all basically is going to become 1, or e to the first, then that means that we're going to have this as negative 4,000 because 4,000 divided by negative 0.1 is, 400 divided by negative 0.1 is 4,000. And again, that's because this is equal to 0. So e to the 0 is equal to 1. That becomes 1. And of course, 8 times 0 is 0, plus the constant, and that's all equal to 0. So that tells us that the constant is negative 4,000.
Wouldn't it be positive 4,000? Carry that.
Yes, it would, because that's negative. You're right. Yes, because that's negative, then this would be positive. Got to watch those signs. So that means the revenue function is actually R of Q is equal to 400 e to the negative 0.1 Q divided by negative 0.1 plus 8Q plus 4,000. And since that gets awkward and aggravating right there, it's easier to actually write and plug in if you just say, okay, 400 divided by negative 0.1 is negative 4,000. E to the negative 0.1Q plus 8Q plus 4,000. And since this is a revenue equation, then this would, it doesn't say, but it's probably dollars. It's probably going to be dollars from selling Q of whatever the product is, because it doesn't give us any further units. Okay?
So that was all A.
That's all part A. Now we need to do part B. So let me get another piece of paper because I have run out of room. So then part B says we need to find the demand function. How do you get demand out of revenue? What's the definition of revenue?
Equals P
P times Q, or it's demand times price, right? Okay. So how's that gonna help us figure this out? Pull these out to the side. So I can line that up better. Revenue equals price times quantity. What do we have? We have revenue. So if we've got revenue and we need the demand function, we need price times the quantity. And since we don't have the price, we need an expression for price, right? So wouldn't that be revenue for a certain quantity divided by the quantity? Wouldn't that tell you how much each one is? This is how much money you make for Q items, and there's how many items it took to make that much money. So that would give you price. So let's take our revenue function and divide it all by Q, and that gives us P. And since price is demand, basically, out of room here again. It's basically that function up there. P is actual to D of Q, so that's actually your demand. So there's the expression for your demand right here. A lot of concepts to remember. Okay? Questions on that one?
Can you zoom out for a second so we can see all of it? Or is that all of it?
It's being recorded, but yeah, I'll leave it up here for a
Okay,
second.
no, that's fine. Thank you.
But again, the tricky part on that one is remembering what demand actually is. Demand is price times the quantity, but demand is also the price. That's the price. It comes from the revenue is equal to price times quantity. And then we've got one more when you're finished with that one. Okay, I don't see anybody still writing. Is everybody done? Questions? Hmm?
Why the price equal to demand?
Because the price, it determines what quantity is demanded. So it's a function of the price, okay?
Yeah.
If you know what quantity is demanded, then that's gonna set a price.
Okay.
So here's our last example, for this section anyway. Then we're gonna go ahead and talk about undoing the chain rule. This one says, find a function f whose graph has a slope f prime of x is equal to 6x squared plus 4 and passes through the point 1, 1. The part we're going to focus on first is find a function whose graph has slope f prime of x equals 6x squared plus 4. Slope is simply the derivative. So if the derivative is 6x squared plus 4, if we take the integral of 6x squared plus 4 dx, we should have at least part of that function. So the integral of 6x squared, keep the 6 out front, add 1 to your power. That makes it x to the third. Divide by that power. Plus, remember this actually used to be x to the z. This is actually x to the 0. 4 times x to the 0 if it helps you think of that. Because 4 times 1 or 4 times x to the 0 is just 4. Basically what you're going to do is you have the integral of a constant is that same constant times the variable. So this is going to be 4x. Just like the derivative of constant is 0 and the derivative of x is whatever's in front of it, then the integral of the constant is 4x. It just puts the variable back. And then of course we have plus c. So what we have at this point is that f of x is equal to 3 goes into 6 2 times 2x cubed plus 4x plus some constant c. Then they gave us another piece of information. They said that this function contains the point 1, 1. That means that f of 1 is equal to 1, and that's the point where x is 1 and y is 1. So that means this is 1. And x is also going to be 1. 2 times 1 cubed plus 4 times 1 plus your constant says that this is 2 times 1 cubed is 2 plus 4 times 1 is 4 plus a constant is equal to 1. And of course 2 plus 4 is 6. So 6 plus your constant is equal to 1, and that means then that your constant is equal to -5. So then we can take that constant and plug it back into our f of x. And that's going to be 2x cubed plus 4x plus a -5, or you can write -5. Either one of those is perfectly acceptable. Questions? Okay, now we're going to talk about unraveling the chain rule. And unraveling the chain rule in the language of calculus is called substitution when it comes to integration. So let's talk a little bit about what that is. If u is equal to f of x, the differential of u, which is the same as the derivative of u, is written as du, and it's the derivative followed by dx. So for example, if we had u was equal to 2x to the third power plus 1, then the derivative of 2x to the third plus 1 is called du, and du would be 6x squared dx, saying that this is the derivative with respect to x, and this function was originally in u. We're only going to use that as a notational device. The thing that you need to take away here is that if we are going to be able to integrate 2x cubed plus 1 raised to some power, which you know is a chain rule problem, right? That's the undoing of a chain rule problem. Then somewhere in this expression we have to have the derivative of 2x cubed plus 1, which means this has to be present for us to be able to do the problem. And what that tells you then is that this is the function that we're actually integrating, and it's raised to the 4th power, and this is the derivative of that function that's been raised to the 4th power. That has to be there, but you don't have to do anything with it once it's there. It just has to be there. If it's not there, you have to figure out some way you can get it there. And that's going to be the place where it's kind of tricky. Just like it was when we did chain rule, you have to figure out what's the inside and what's the outside so that you know how to take the derivative of the inside. Well, here, we're going to have to be able to look at the function and know what was the inside and make sure that we have the derivative of that inside as part of our integral. So we're going to do an example of this problem, and I've actually already got this one worked out so that I can just explain rather than actually do the problem with you. So if we were given this problem, then what we look at, trying to solve it, is okay, this is the function that was part of the chain rule. In order to be able to proceed, we need the derivative of that function. And the derivative of that function is 6x squared dx. The dx just indicating that it's a derivative. Once we know that we've got that, we're basically treating that as du. And what we're actually going to integrate is a function raised to the fourth power. This is the function, but we're going to ignore it for the time being and just concentrate on the power. So what we do is, and this is why they call this the u substitution, that's being treated as u, and this is the derivative of u, is that 6x squared dx. So if I'm taking something raised to the fourth power and I'm integrating it, what I do is I add 1 to the power. Four plus 1 equals 5. I keep that same value that was inside there, I put it back in there, 2x cubed plus 1. And then, just like I do with any other power, I also divide by that power. So as long as what you've got includes the derivative of whatever you put the power on, or whatever you've taken a square root of, or whatever that's being done to that function, as long as you have the derivative of that function as part of your integral, you're good to go. Just actually do the integration of that function. But sometimes you don't have everything you need. So here's an example of what if you don't have everything you need. Find the integral of 6x times the quantity 3x squared plus 4 raised to the 7th power. What would you consider the inside function here to be? Yeah, it kind of jumps out at you. It's actually easier to recognize these for the most part in integration than it was when you were doing chain rule. So this is your u function. This is the function that's actually being worked on. So we're going to do the integral of u raised to the 4th power. Or I'm sorry, to the 7th power. Raised to the 7th power. But before we can do anything else, we have to make sure we have du. Do we have du? Now what we haven't used so far is we haven't used the 6x and we haven't used the dx. And the question is, does that equal the derivative of u? Now, if this is u, what is the derivative of u? Six x plus 0. And then the dx just indicates that is a derivative with respect to x. So, does it? The answer is yes. So we've got this, therefore the only thing we're going to worry about is this function raised to the 7th power. So the integral of that function raised to the 7th power, we're going to add 1 to the power and make it 8. Then we're going to divide by 8. And the value of the function itself then is just what it started out being, 3x squared plus 4. And that's it. Add your constant and you're finished. Any questions? Nothing. It had to be there so you could use it, but then once it's there, you don't really need to use it. It just has to be there to make you able to do this. You just have to verify that it's there. Okay? Now, I'm gonna present the next one in a little bit different way from what is actually presented in the book. So here's what your next one's gonna look like. This is example 2. Sorry, wrong way. And we want to take the integral of that function. What do you think u is? Think that's it? Think it's x cubed plus 1? Okay. Since we don't have anything that we can do with radicals, what are we going to do to change that to something we can do anything with? Pull it up to the top and call it 1/2 power, right? So there's our function raised to the 1/2 power. And we want to integrate that function. But the question is, do we have the derivative of that function? So that's going to be the first thing we're going to have to think about. What's the derivative of x cubed plus 1? 3x squared. So now let me pull this back down and look, back out a little bit. Do I have 3x squared dx? Because remember, it's actually 3x squared dx, indicating that is the derivative. Do I actually have that? What am I missing? I'm missing the 3. So I got the x squared, no problem. Got the dx, no problem. But I'm missing a 3. I need that 3. I can't do the problem if I don't have that 3. How can I put in a 3 and not change the value of what's there? It's going to seem like trickery when I do it. I can, but now I've changed the value of the integral. Or maybe multiply it by 1/3. Okay? So is the net result of what I just did no change? Yeah. If you have to add a constant, put the constant in there. Then put 1 over the constant out in front. If that constant's a fraction, flip that fraction over after you put it in and put it out front. Basically, you take the reciprocal of what you need and put it out front, and what you need on the inside. Because now that I've got that, I have du. Because this is du. Once I've got it, I don't need it anymore. I had to put it in there. But now that I've put it in there, I've added something that I'm going to have to contend with when I actually do this problem. I've still got that 1/3 sitting out there. Okay? So you got to keep it. It just hitchhikes along like any other coefficient, but you got to keep it. You're going to need it. So then your integral is going to be 1/3 for that one that was out in front to start with. Then we need the derivative of this function raised to the 1/2 power. So that means we need to add 1/2 plus 1, right? Which is 3/2. And we're actually going to divide by 3/2, and I'm going to write it that way to start with. And that's going to be plus a constant. Then I'll put the function back inside. And this is actually the right answer, and there's nothing wrong with it. But if you're trying to enter it into MyMathLab with those fractions and, you know, everything that's entailed, you're gonna have to enter a lot of parentheses or open up a lot of fractions to make this work. The easier way to write this is to remember, and we've done this before, if you're dividing by 3/2, it's the same thing as multiplying by 2/3. And honestly, we're including the C in that multiplication. We'll talk in a minute about why that really doesn't matter. So what's 2/3 times 1/3? 2 times 1 is 2. 3 times 3 is 9. And then that's times x to the third plus 1 to the 3/2 power plus 2/3 times the constant. Now, if we don't know what that constant is, does it make any difference if we multiplied it by 2/3? Well, no, it's still a constant. We still don't know what it is, so we'll just put down C. Now, if they gave us a point on that original function like we had a minute ago, then we could plug in and figure out what that constant was, but we don't know. But the fact we've multiplied 2/3 times that constant, it doesn't change the fact that we don't know what it is, and we're just gonna put a letter down for it. Okay? It doesn't change anything. Now, there's actually two different ways to do it. In the PowerPoint that I have probably posted, it shows you a different way, but to me, this is the most straightforward way. If you look at the other way and you understand it, or you would like to understand it, ask me, and I will explain it to you. But I've always been of the opinion there's no point showing somebody two different ways to do something if one of the ways is harder than the other. And I think this is the easier of the two ways. Now, there is a little caution that you need to know about here. And this is very important. Too far. What did we actually put in last time for that U substitution? What did we have to actually add in? We added a number, okay? We dropped in a number. And we undid dropping in that number by also dropping in its reciprocal. You can't do that if you've got this kind of a situation. That won't work. If we're trying to take the integral of x cubed times, and I just put the parentheses in there for emphasis, times the square root of x cubed plus 1 dx. Here's our u. And it's raised to the 1/2 power. The question is, what's du? So you look at what we think u is, which is x cubed plus 1, and tell me what its derivative is. Okay? This is the derivative of what's in there. This is what I've got to work with. I can drop a 3 in there, no problem. Put a 3 here and a 1/3 on the outside. But I need another x. Is there any way to drop an x in and take it back out? You can drop in constants all day long. You cannot drop in variables. So as far as you know, that problem is not possible. Now, the truth of the matter is you can integrate that, but we're not going to do it because we're not going to get into the more advanced techniques of calculus that you would need to be able to do it. But you can't do it by substitution. That's the point. You cannot do it by substitution. It requires a method that we're not going to learn. So I'm not telling you it can't be done, only that you can't do it with the tools you've got. Okay? And then the hardest part, and I'm remembering when I was in calculus the first time, this actually, just like chain rule, when you first do chain rule was hard. It was really hard because you had to figure out what that inside function was. But once you've done chain rule for a little while, chain rule got easier, and y'all been doing chain rule and doing just fine for a long time now. Well, this is the same way. Don't expect the U substitution to be just something that drops into your mind like magic. It's going to take practice. So if you have to spend a few extra minutes on this kind of problems, don't sweat it. There's nothing wrong with you. It just takes a little bit longer to do problems with substitution because you have to be very careful that you've got your correct derivative before you can ever do the problem. So we're going to do one more example at least, and then we're probably going to call it a day and go eat turkey. So here's example 3. I do have some others, but I'm saving them for after Thanksgiving. So I'll have something to bring your mind back together again. This one's a little bit tougher. So we've got the integral of x plus 3 over x squared plus 6x quantity squared. And just like I normally would if I were doing anything else, first thing I'm going to do is try to rewrite that into something that I think will be easier to work with. So first of all, I don't like that being in the denominator, so I'm going to give it a negative power and put it in the numerator. That way I don't have to deal with rational expressions. And then I'm going to keep the x plus 3 up there also because apparently I'm going to need that. And then I'm going to leave the dx. So all I did was I split that rational up into the product of something with a negative power times the numerator. What do you think u is? Is it this or is it that? What makes you think it's that? And you're right, but what makes you think it's that? Well, that one has a power 2, but its power is 1. Okay? I look for things that have powers that are not 1. And if it's not 1, that makes this more complicated in my brain. Therefore, this must be what u is, because u's always the one that's complicated. It's always the one that has issues. So I'm going to treat this as if it were u. So if that's u, and it's u to the negative 2 power, what's du? And then, of course, it has the dx at the end of it. So, do I have du? Do I have 2x plus 6? No. Could I make 2x plus 6 out of what I've got?
Does it
Mhm.
dx?
Yeah, it says dx. Trying to keep it big enough to read and keep it on the screen, that's challenging sometimes. What do I need to go with this to have that? I need a 2. So I can put a 2 in there. But if I put a 2 in there, where else do I have to put something? Outside, I gotta put 1/2. So that means I'm gonna have to keep that 1/2. I need the 2 to make 2x plus 6. But now I've got something I can work with. Because now I have 1/2 times the integral of u to the negative 2, and this is du. Now that I know I've got it, I pay no more attention to it. I needed to recognize that I had it and make it happen to know what I need to put out front. After that, I'm done with it. I don't need it anymore. So this is going to be u to the negative 2 plus 1 over negative 2 plus 1, which is negative 1. And it's going to be multiplied out front by 1/2. And since negative 2 plus 1 is negative 1, then this is what it actually looks like. U is x squared plus 6x to the negative 1 power over negative 1, which I'm going to pull that negative 1 out here and just change that 1/2 to being negative. And negative 1/2 times this is the same as saying the opposite of that over 2. Now that's not too hard to type in to my math lab, but the equivalent expression would be negative 1 over 2 times x squared plus 6x plus your constant. Either one of those would be fine. You can leave the negative power and the negative sign out front, or you can drop the negative 1 power, put it down in the denominator with the 2, and leave negative 1 up top as a placeholder. Either one is just fine. Any questions? As long as you are very careful that that's exactly what you put in. My math lab's actually better at it than trying to put it in the graphing calculator, because graphing calculator you'd have to have bunches and oodles of parentheses. At least my math lab does fractions the way they look. So it should take either. If you get stuck on anywhere you're trying to put in an unsimplified one and it's not taking it, you know, look and see if you can tell if what you've got is equivalent, then just tell me I need credit for number so-and-so. Or if you can't tell if it is or not, just click Ask My Instructor and ask me to check that one, and I will. Okay? Any questions? Okay, when we come back, we have 2 more. No, 3 more. We have 3 more. And then, excuse me? No. No. I only show one way to do the substitutions because to me the other way is confusing. I understand it, but I know a lot of people that don't think like a math person, don't understand it. So I'll leave that method to the engineer. Okay, I hope you all have a happy Thanksgiving. Please complete your quiz. Please try to get your homework at least attempted for all of chapter 15, not everything that's there, but for 15.1 and 15.2, at least get it attempted in show me so I can tell if you're on the right track or not. Okay? But beyond that, don't think about calculus until after you eat a lot of turkey, like maybe Friday or Saturday. Watch football. you